Well, it's time we learn about solar radiation and Earth's seasons. Let's go. So let's start with this. Uh, all objects in the universe give off light. You give off light. I give off light. A pencil gives off light. Everything. There's nothing in the universe that doesn't. And here's why. Light is made anytime you take a charged object and you wiggle it. And since atoms contain electrical charges and all objects have thermal energy, which makes them wiggle, therefore all objects are going to be giving off light. Now, the hotter an object is, the faster it wiggles, and the higher frequency, shorter wavelength light it gives off. So objects that are very hot, like say the sun, their atoms are wiggling very quickly, so they give off these high energy, short wavelength light that we call ultraviolet, but also visible and some infrared. But objects like you and me and the Earth that are cooler, their atoms are wiggling slower, so they give off longer, low energy waves, which we call infrared. So you give off light, it's infrared light. When you walk into KIS in the morning, that detector, that little camera that tells you whether you got a fever or not, it's observing the type of infrared light you're giving off. So you glow in the dark, and these sensors are able to detect it. Now, we've talked about this before, but it's an important concept, so let's talk about it again. It's called the first law of thermodynamics. The first law of thermodynamics, which I would argue is one of the most important laws in the universe, says that energy can never be created or destroyed. It is conserved, meaning if an object loses energy, that energy must go to somewhere. It doesn't just stop existing. That the energy of the universe is a constant amount. It can move from one object to another. It can take different forms: heat, light, stored as food energy. But the total amount of energy always stays constant. So when an object absorbs light energy, that light energy goes away and it becomes manifest as the jiggling of atoms. So it's kind of interesting. So when light shines on an atom, it makes the atom jiggle. But when an atom jiggles, it gives off light. So there's this interplay between light energy and thermal energy. And that's going to be really important as we look at things like global warming. So when atoms vibrate, they give off light waves, but when atoms absorb light waves, they start to jiggle. So if an object absorbs 1 joule of visible light, then it has to gain 1 joule of thermal energy because I can't destroy that energy. If an object gives off 1 joule of infrared light, then it's going to have to lose 1 joule of thermal energy. In other words, the total amount of energy stays constant. It can just get moved from, say, thermal to light and back and forth. It can take other forms, but for today, we're just going to look at those two. So the sun is releasing energy stored as nuclear potential energy. So there's uh, uh, nuclear reactions happening in its core, and the outside surface of the sun that faces us, it's at a temperature of about 5,000 degrees Celsius. So at 5,000 degrees Celsius, or 5,500, you mostly give off ultraviolet and visible light. So as ultraviolet and visible light travels through Earth and travels through space rather, and it hits the Earth. Well, when that light energy hits the Earth gets warm, and those atoms of the Earth shake faster. So the Earth overall is at about a temperature at its surface of 15 degrees Celsius, which means it's going to give off infrared light. And so that infrared light is going to leave the Earth and go into space. And so later on in this year, when we talk about global warming, it just has to do with how much energy comes in as visible light versus how much leaves as infrared light. Now, when it comes to the sun, the amount of sunlight that hits the Earth is pretty important amount to know. So it turns out that if the sun's rays come in perpendicular and we have the maximum concentration of solar energy hitting a given square square meter of Earth's surface, what we find is that there is 1,000 joules of light energy that strike every second on each square meter of the Earth's surface. So for in every second, 1,000 joules of energy, or 1 kilojoule, hits each square meter of Earth's surface every second. Now, 1 watt, you've probably heard of watts. Well, 1 watt is basically a measure of power, the rate at which energy is transferred. So 1 joule per second is the definition of a watt. So if I transfer 1 joule per second, that's 1 watt. Well, at the most, the sun is able to transfer 1,000 joules or 1,000 watts so 1,000 joules per second to every square meter of Earth's surface. Or in other words, The solar constant, we'll call it, is 1 kilowatt per square meter. And that's the maximum that the sun can give us, no more than that. But it can give us less than that. And here's why. So when sun's rays, and this is a very important concept, so please focus in on this. When the sun's rays, like this flashlight, are coming in perpendicular, then the light is as concentrated as it can get. It's condensed into the smallest unit of area that it can. So if this was the sun, I would have 1,000 joules per second, 1,000 watts hitting a square meter of surface. But if you take it at an angle, what happens is that same 1,000 watts is now spread out over a greater amount of area. So you have less joules per second in every given unit area. So as the sun strikes at lower and lower angles, it's delivering less energy to each square meter. And that's a very important idea in understanding the dynamics of the energy flow on our planet. So I don't know. I mean, this makes sense to me. Hopefully, it makes sense to you. We'll see. So here's the idea: if the rays are coming in at 90 degrees, that's straight down, like concentrated as you can get. Then what we find is I take 1 square meter. Here it is. Here's a square meter, and what I find is the energy density is 1,000 watts per square meter. In other words, every second there's 1,000 joules of energy hitting this square meter. But if I took the rays and put them at a 30-degree angle instead, well, if I take the sine of 30, I get zero point 0.5. So what that means then is these rays are now spread out. Instead of over 1 meter, they're spread out over basically 1 meter divided by zero point 0.5 is 2 meters. So now I've spread them out over 2 meters. So instead of the sun rays looking like this, now I've got to spread out over 2 meters. I suppose I should turn this sideways. So now I've got 2 square meters, which means I have half as much energy. I have 500 watts per square meter instead of 1,000. So you can see that by tipping the sun's rays at a 30-degree angle, I have half as much energy delivered to each square meter of surface, which means it's not going to get as hot because energy absorbed gets turned into thermal energy. So this surface of the Earth would get twice as hot as this surface would because I've spread the energy out over twice as much, the same amount of energy spread out over twice as much area. It means each unit of area gets half as much energy delivered to it. So if we look at the Earth, what we see is near the equator, the sun's rays tend to come in pretty close to perpendicular. So that energy from the sun is concentrated in a very small area. But as we move towards the poles, the light comes in at more of an angle and it gets spread out over a greater area. And therefore, that explains why it's hotter at the equator and colder at the poles, because the energy is more concentrated. There's more energy per square meter at the equator than there is as I get closer to the poles. And this can help us understand why Earth has seasons. Now, the reason Earth has seasons is because our rotational axis, the north and south poles about which the Earth rotates, are not perpendicular to the plane of orbit, which we call the ecliptic. Instead, they're tipped at 23.5 degrees to it. And so what happens is, because of this angle tip, there are times of the year where the sun will appear higher in the sky, the summer, and there's times of the year where it'll appear lower in the sky, winter. And the amount of deviation is it's 23.5 degrees higher in the summer and 23.5 degrees lower in the winter, which makes a pretty significant change in the overall amount of area that the sun's rays are spread out over. So basically, what we find is as the sun goes around in its orbital path, we find that in the summertime, the pole is tipped towards it. Now you got to keep in mind the southern and the northern and southern hemispheres have opposite seasons. So during the summertime in the northern hemisphere, our axis is tipped 23.5 degrees towards the sun, which puts the sun 23.5 degrees higher in the sky, which makes the sun's rays more concentrated, makes it warmer. But at the same time that's happening in the southern hemisphere, the sun is 23.5 degrees lower in the sky, which makes its rays more spread out, which makes it colder. Now, for us, in December, we're tipped away 23.5 degrees away from the sun, which makes the sun's rays more spread out and less concentrated and therefore colder. There's less energy per square meter in the wintertime. But at the same time that we're having our winter, the axis is 23.5 degrees towards the sun in the southern hemisphere, and now their rays are more concentrated and they're experiencing hotter weather, and therefore it's summer there. So here is a depiction of the Earth going around. So what we find is it's best to talk in terms of the time in which the axis is tipped most towards the sun or most away from sun is referred to as the solstice. In the June solstice, which happens around June 21, June 22, the axis is tipped at its greatest angle towards the sun, 23.5 degrees towards the sun. The North Pole is. In December, the northern axis is tipped 23.5 degrees away from us. So we call it the December solstice. Now, sometimes we'll say summer solstice and winter solstice, but you have to understand that is hemisphere specific. All right. So when we say this would be our winter solstice, this would be our summer solstice. But in the southern hemisphere, this would be their winter solstice, and this would be their summer solstice. Solstice just means the day at which the axis is tipped at its most towards the sun, being 23.5 degrees. But as we go from 23.5 degrees away from the sun to 23.5 degrees towards the sun, we reach this midpoint. And we call this the equinox, which really means equal days or equal nights. All right. And basically, what happens there is at that day, which happens March 22nd and September 22nd, the axis is neither tipped towards nor away from the sun. So therefore, the sun's position in the sky is equal to whatever your latitude is. And so on these days, we find that the days and nights are of equal length, whereas in the wintertime, our days are shorter, and in the summertime, our days are longer. More on that in a second. But on the equinox, they're the same for everyone on the planet. Everyone on the planet on the equinox has a 12-hour day and a 12-hour night. 12-hour day, 12-hour night. But here, it can be very short, and here it can be very long. So at noon on the equinox, the sun's position in the sky is equal to the latitude of your location. So if you are at a latitude of 40 degrees north of the equator, at noon on the equinox, the sun is going to be 40 degrees up in the sky. And we could take the sine of 40 degrees and figure out just how much of that 1,000 kilojoules per square meter you're getting. But what happens is, yes, on the equinox it's at 40 degrees, but at winter solstice, if we're in the northern hemisphere, which I believe we said that would be December 21st, then the sun is going to be 23.5 degrees lower in the sky than that, which is 16.5 degrees. That's really low. Those rays are really spread out. Therefore, it's cold. And in the summertime, it's going to be 23.5 degrees higher than that. So the sun will be up 63.5 degrees in the sky, which makes its rays a lot more concentrated. And that's why it's hot in the summertime. Makes sense, right? So it's warm in the summer because the sun's rays are higher. Now, this is June, so this is in the northern hemisphere. The rays are concentrated in a smaller area. In the wintertime, they're spread out over a larger area, so there's less energy being delivered to each square meter. But there's another important thing to keep in mind, and that is during the summer, the sun is up for a longer time. You might have noticed recently that the sun is, you're starting to go to school in the dark. You're starting to come home and it's getting dark. Where in the summertime, it's been light a long time before you came to school, and it's light a long time after you come to school. That's because there's quite a difference. So in Seattle, where I come from, we have 16 hours of daylight in the summer, but only 8 hours of daylight in the wintertime. That's a huge difference. And so basically, I have half as much time that the sun is shining, and the sun is shining at a significantly lower angle. So those two things compound the effects. In the wintertime, I have weaker light at a lower angle for less time. In the summertime, I have more concentrated light at a steeper angle for a longer time. This graph is kind of interesting. So if we look at this, we're going to take different locations. So it's worth noting that at the equator, every day is 12 hours every day of the year. It never varies. As you move away from the equator, you get greater and greater extremes. So if we go to, say, 35 degrees north, we see that the length of the day can go from 9 hours in the winter to like maybe 17 hours in the summertime. If we go to 50 degrees, it becomes more extreme than that. If we get to 66 degrees, wow, it's really huge. And if we go to the North Pole, basically at the North Pole, it's night And then there's one day when the sun comes up and it stays up for 6 months and then it goes back down for 6 months. Pretty weird to think about, isn't it? All right. But on the equinoxes, which is here and here, which is the March 21st and September 21st, notice everyone in the world has a 12-hour day. And that's because on this day and this day, the axis is neither tipped towards nor away from the sun. And so everybody gets the exact same amount of time, and the sun's position in the sky is exactly equal to your latitude. Now, we have different regions of the planet. We refer to them as the equator. We have the Tropic of Capricorn and the Tropic of Cancer, to the tropics. And then we have the Arctic Circle and the Antarctic Circle. And you will be surprised to know, not really, that the numbers you need to know are 23.5 degrees. If you go 23.5 degrees above the equator, that is what we call the Tropic of Cancer. So the tropics are between 23.5 degrees. Remember, that's the tip of the axis to the equator. And the Tropic of Capricorn is between the equator and 23.5 degrees south of that. And why these are important is if, remember, uh, that if the sun is tipped here, it's 23.5 degrees higher in the sky than north. So if you're at 23.5 degrees north latitude and the sun is 23.5 degrees higher than that, what basically that does is it puts it directly over your head. So if you are within the tropics, there's at least 2 days during the year. Well, I should say at least one day if you're at the exact tropic line, where the sun is going to be directly overhead. So this is the region of the planet where the sun is sometimes completely coming straight down, delivering its maximum 1,000 watts per square meter. Now, when we get to the Arctic and Antarctic circles, so if you're in the Antarctic circle, which is 23.5 degrees south of the pole or 23.5 degrees north of the South Pole, these are regions where you can have 24 hours of daylight and 24 hours of night, depending on what day of the year. So what we find is that when I tip the sun, I tip the Earth 23.5 degrees towards the sun, then that 23.5 degree line right here tells me that if I'm in this region here, as I go around the axis, the sun never sets. Here, the sun never comes up. So the Antarctic circles and Arctic circles are 23.5 degrees away from the poles, and the tropics are 23.5 degrees away from the equator. So the thing about in the equator, I'm sorry, in the tropics, there's going to be 2 days out of the year where the sun is directly overhead and your shadows are kind of weird looking. I love these pictures. If you've ever been there, it's pretty wild. I had a chance to be in Bali close to this day, and it was quite remarkable. Now, it's worth noting that the southern hemisphere experiences its winter at the exact opposite time that we do. We've already explained that, so I'm not going to go into any more detail here. And the last thing to say is the primary productivity, which is also linked to biodiversity, it should not be surprising that it is related to the amount of radiation absorbed by the sun. So we find that in the tropics is where we're going to get the most light energy hitting the Earth's surface. So that's where we're going to be able to have the most productivity, and that's therefore the most food, and that allows us to have the most biodiversity. And as we move away from that, we find that productivity decreases, and so does biodiversity. Okay, that was a long one. I'm sorry. Hopefully it made sense to you. We'll see how you do when we work through some of the problems.